We're looking at lesson 4.03 today, solving equations literally. Today's objective is I can solve a literal equation for a given variable in 2 out of 2 problems. Remember last lesson we talked about what literal equations are. They are equations with more than one variable in them. So when we solve them, we're solving for a particular variable that they tell us to solve for. So we're going to warm up with a couple of equations to solve. It says solve these two equations for x and then asks how are they the same and how are they different. So let's see, we have this equation, we have this equation. They look kind of similar in some ways. Let's look at this first one, how we might solve it. We're going to draw our line, circle our variable, highlight our other terms. So we have our multiply by 3 and add 2. And we ask, what is the furthest term highlighted from x? Which one is further away? Well, this one's further away. That 3 is really close to the x, so we're going to do the inverse operation to get rid of it. We are currently adding 2, so now we're going to subtract 2 from both sides. Subtraction is the inverse operation of addition. The plus 2 and the minus 2 will cancel, and we get 3x equals 14 minus 2 is 12. We have one more step to get rid of the 3. We're currently multiplying by 3, so now we need to divide by 3 on both sides. That's the inverse operation of multiplication. These 3's cancel, and we get x equals 12 divided by 3 is 4. All right, so let's try this one over here. This is a literal equation. Now we have two variables, x and y. But we will start it the same way. We'll draw our line, circle our variable, highlight our other terms on the same side. And now we ask, which term is further from x? Is it the 3 or is it the 2y? Well, the 2y looks like it's further away, so we need to do the inverse operation to get rid of it. We're currently adding 2y. Now we'll need to do the inverse, which is subtract 2y. Notice that this whole term can be subtracted. We don't need to divide by 2 or get y by itself. We can just look at this as a whole term by itself that we need to get rid of. So we'll just subtract 2y from both sides. That 2y and that 2y will cancel. We get 3x equals, now notice we can't simplify this at all, so we just get 14 minus 2y. And then our last step is to get x by itself. We're multiplying by 3, so we will divide by 3, inverse operation. None of this over here can be simplified, so we just get all of that stuff brought down. X equals 14 minus 2y over 3. So that's our solution on this side. X equals 4 was our solution over here. So how are these two similar? What do you notice? Well, you may have noticed that they have the same numbers in all of these places. The 3, the 2, and the 14. So they have the same numbers. What about our solving? Are they similar in any way in how we solve them? Let's see, we had a subtract step right here. Subtract 2, subtract 2y. So the only difference there is that there was a y. And then down here we have the same step as well. We had a divide by 3. So we have the same or very similar solving steps too. How are they different now? How are these two equations different? What do you notice? Well, it looks like this one has a y, so one has a y value. And what about our answers? How do our answers look different? Well, the one that has a y couldn't be simplified. We couldn't simplify it down to a single number. So we just ended up with an expression in terms of the other variable. And that's really common when you have literal equations, to get kind of a fraction or an expression that can't be simplified. It's just going to be what it is. So great warm up. Now we will get going on today's lesson. We're going to be looking at some properties for solving, and actually almost none of these will look new. All we're doing today is just giving them names. Giving them names you maybe haven't heard before. So the first ones we're going to look at are called properties of equality. These are things that you can do on opposite sides of an equal sign. So for example, we can add to both sides of an equal sign. This is called the addition property of equality. So look down here, we have x equals y. If we add z to both sides, that doesn't change the equality. These things are still equal. We know that we can add z to both sides. So x plus z will be the same thing as y plus z. Right? This is a property we've used a lot. So what other properties of equality can you think of? What else can we do to both sides of an equation? We can add to both sides. What about subtract? Does that work? It sure does. We have a subtraction property of equality, which I will abbreviate as POE, so I don't have to write that all out every time. What else can we do to both sides of an equal sign? What about multiplication? We can multiply on both sides of an equal sign. It doesn't change the equality. And division. Does division work? We can divide both sides by 5 or by x. Division. Actually meant that to say division, not divide. There we go. Division property of equality. All of those are valid properties of equality. We use them all the time in solving, we just haven't given them names before. All right, how about the distributive property? This might sound familiar. You might have seen this before, or maybe you haven't. What does the distributive property tell us when we have parentheses like this? Well, it tells us we can distribute the a to each of these terms inside the parentheses. So this becomes a times b plus a times c. Remember, there's an implicit multiplication in here. We don't always write that multiplication symbol, but we know it's there. So we distribute that multiplication between the a and b and between the a and c. So specifically, this is called the distributive property of multiplication over addition. Lots of words there. But why do you think we might call this multiplication over addition? Well, we are doing some multiplying and we're doing some adding. Let's see, we have multiply here. And we're going to multiply over the parentheses and multiply this over the parentheses as well. So if you look at this literally, we have literally multiplication that goes over the addition. The multiplication is going over the addition that's happening inside the parentheses. So this is the distribution of multiplication over the addition that's happening inside the parentheses. Now what if there were a subtract in here instead? Is that valid? Can we do distribution over subtraction as well? We sure can. That is another thing, that there is a distributive property of multiplication over subtraction. It works exactly the same. We have a multiplication here, and we distribute the a to the b and the a to the c, and we get a times b minus a times c. Now we have things called identities and inverses. about what the word identity means. You have an identity as a person. All people have an identity. What does identity mean to you? Is it maybe your physical characteristics? It could be your mental characteristics. It could be your personality. All of those things identify us as individuals. Well, we can think of numbers as having an identity as well. Like the number 3 has its own identity that's different than the number 4. And this variable here, a, has its own identity. We don't know what number is living inside of it, but it has its own identity that's unique and different from all other numbers. And so what we mean by the additive identity is a number that we can add to any other number, and it stays the same. It keeps its own identity. It is still unique and wonderful number 3. It hasn't changed at all. So if we take a plus 0, what do we get back? Well, a plus 0 is a. Anything plus 0 equals itself, right? So that's why we call it the additive identity. 0 is the additive identity because anything gets to keep its own identity. It says, I'm still a. Even though you added 0 to me, I'm still a. I'm still the same individual identity I was before. So then we have this additional idea of an additive inverse. Anything plus its opposite equals what? A plus negative a, what will that equal? Well, that equals 0. Notice 0 is the additive identity, so this is sort of the inverse idea. We take any number plus its opposite, and we get the additive identity back. And we can use these properties, we use them all the time in solving, because it helps us eliminate numbers. So if we have something like 3x plus 2 equals 5, we know that this plus 2, we can add a negative 2, also known as subtract, to both sides using this, and we know that that plus that will equal 0. This plus this will equal 0, so 3x plus 0 equals 3. But now we also know, because of the additive identity, that 3x plus 0 is just 3x. So we have been using these properties this whole time. They've just been less explicit. We haven't put a name on them. So if we have an additive identity and an additive inverse, what about multiplication? Can we apply that to multiplication? Yeah, we sure can. We have a multiplicative identity. Is there a number we can multiply a by to get itself back? Anything times what equals itself? Well, that number is 1, right? A times 1 equals 1. Or sorry, a times 1 equals a, rather. Anything times 1 is going to be itself. So that makes 1 the multiplicative identity, similar to how 0 is the additive identity. Now the multiplicative inverse is a little bit more complicated, and this might be a new idea. But the multiplicative inverse is going to be the reciprocal. That means the fraction flipped upside down. So we have a over b here. If we multiply that by the fraction flipped upside down, b over a, we're going to get 1. Let's see how this works. So say we have like 2/3, and we want to multiply that by its reciprocal. That's going to be 3 over 2, so the fraction flipped upside down. Now if we multiply this straight across, we get 2 times 3 is 6 on top, 3 times 2 is 6 on bottom, so 6 over 6, and that is going to equal 1. And that is true for any fraction as long as both of these numbers aren't 0, because we can't divide by 0. What about, say, the number 4? Does the number 4 have a reciprocal? Is there a number we can multiply it by to get 1? It might not look like a fraction at first, but there's always this hidden 1. An implicit 1. We can turn whole numbers into fractions by putting them over 1, because 4 divided by 1 is still 4. So our multiplicative inverse here will be fraction flipped upside down, 1 over 4. We'll get 4 on top, 4 on bottom, and we still get 1. 1 is our multiplicative identity. So we can always use this multiplicative inverse as well to get rid of any number we're multiplying by, including fractions, especially helpful for fractions. So here is a summary slide. This is a great one to take a picture of for your notes. This will summarize all of the properties we talked about today, all of the properties of equality, the distributive properties we talked about, and the identity and inverse of both additive and multiplicative properties. So let's see how we use these. It says to solve for x, but now we have this additional thing. It says justify each step with a math property. So what we're essentially doing here is a proof. This is a very formal way of proving something mathematically. And we don't often do this in algebra, but we can. This is usually something we do more in geometry or calculus, but we can do it in algebra. Let's see how it would work. So we're solving for x. I'm going to draw my line, circle my variable, highlight my other terms that we need to get rid of. What should we do first here? Maybe I see parentheses. I always like to distribute. So let's distribute here. Bring the 45 down. 5 times x will just be 5x. We have a subtract. We're going to distribute over subtraction. And then 5 times 5 is 25. So we have 5x minus 25. But now we need to write down what step we used here. So this was the distributive property. Distributive property. Okay, so our next step in solving, we're looking for what's furthest away from x. Looks like this minus 25. So we'll add 25 to get rid of it. Add 25 to both sides. These 25s cancel. We get 45 plus 25, I believe that's 70, equals 5x. And now we have to justify the step we just did. Add 25 to both sides. Well, what property says we can add the same number to both sides of an equal sign? That is the addition property of equality. Okay, our last step here, we're getting x by itself, so we have 5 times x. We do the inverse operation, we divide by 5, divide both sides by 5. What property says we can do that? We can divide both sides of an equal sign. Well, dividing says it's the division property of equality. These 5s will cancel. We get 70 divided by 5 is 14, I think. And then we're just left with x. So that is our solution. 14 equals x. And we now have a proof that justifies why we can take each of those steps. Let's try another one. Okay, this is a very similar equation to the one we just solved, only this one has a y now. This is a literal equation. We are again going to solve for x and justify each step. So yeah, I draw my line, circle my variable, highlight my other terms. What should I do first here? Well, distribution worked out well for us before. Maybe we'll try that again. So we're going to use the distributive property. See, on the left side we have 45. On the right side we have 5 times x. That's going to be 5x. We're going over subtraction. 5 times 5 times y. Well, 5 times 5 is 25 times y. All right, we are once again getting x by itself. Maybe I'll highlight my other terms again, see what we need to get rid of. Which one is furthest away from x here? It is minus 25, so we need to do the inverse operation. What's the inverse operation of subtract? Well, it's add. We're going to add 25y. Notice once again, we can take this as a whole term. We don't need to divide by 25. We don't need to get y by itself. We can just take this as a whole term by itself. Like any other number, we're going to add 25y to both sides. And why can we do that? What property lets us add the same thing to both sides? We add, so it's the addition property of equality. These 25y's will cancel. We can't simplify the left side over here because we can't combine those terms, but that's okay. We can just leave it as it is. Now we have 5x on the right side. We just need to get x by itself now, so we're going to divide both sides by 5. What property allows us to do that? Well, we divide, so it's the divide or division property of equality that lets us do that. These 5's will cancel. On the right side, we just get x. And then 5 actually divides evenly into those, so we can do that. 45 divided by 5 is 9. And then 25 divided by 5 is 5, and the y comes down. 9 plus 5y is our answer. And this is our proof. So this is similar to the one we just solved, except we got a number, right? We had very similar steps. We go back to the previous one, we added 25 and we divided by 5. In this one we added 25y and divided by 5. Same steps, we just weren't able to simplify it as much in the answer. So let's skip this one. And we're just going to practice solving literal equations now. We're done proving, we're done justifying all those steps, but we know that we can use all those steps. We're just going to do a few more practice problems now. So let's start with this one. Solve for h. This is the area of a triangle. This is a formula that gives us the area. So area is 1/2 times the base times the height. So when we have a triangle, looks like that. This length is b. And then we have a height right there. And the area is 1/2 times the length of b times the length of h. They want us to solve for h. So we're going to circle our variable, draw our line, highlight our other terms. So now we have a 1/2 and we have a b. Now what are our inverse operations here? Well, I guess we have to figure out what the operations already are. What operations are happening here? They're implicit again, we can't see them. But we have b times h, right? b times h, and then 1/2 times b as well. Multiplication is the operation that's happening here. So we need to divide that, right? That's our inverse operation. So we could try dividing, since we're getting h by itself, we could try dividing by 1/2. But now we have this mess that is a fraction over a fraction, creating a bigger fraction. It's just too many fractions to kind of mess with, right? That makes my brain hurt. It's kind of a lot of fractions. If we think instead, let's undo that. Let's think back to our multiplicative inverse. Our multiplicative inverse said, we can flip this fraction upside down and then get back 1. And anything times 1 is itself, so we should just get b and h, right? So let's try that. Let's flip this fraction upside down and multiply. We have to do it to both sides, right? Multiply both sides by 2/1. These 2's will cancel, these 1's will cancel. 2/1 is just 2, so this is 2 times a, 2a. And what are we left with on the right side? B and h, just b times h. So that's way simpler than this fraction over a fraction business we had before. 2a equals bh. And we're still solving for h, so what's our last step here? Well, we're multiplying by b, so now we're going to divide by b. Divide both sides by b. The b's will cancel. We are left with just h on the right side. And on the left side, we get 2a over b. That is our solution. Notice it's not any simpler than our original equation. When we solve literal equations, it really just means we've manipulated it. We've moved the variables around so that a different variable is by itself. So here we have h by itself. h equals 2a over b. So let's look at another one. Now this is the equation for degrees Celsius to Fahrenheit. So these are both ways of measuring temperature that are used in different parts of the world. In the US, we typically use Fahrenheit in most places. In a lot of other places in the world, they use Celsius in Europe and other places. So this is the formula you can use to convert Celsius, degrees Celsius, to Fahrenheit. And they want us to solve for C. We're going to go the other direction now. We want to get C by itself. So we can do the other conversion, converting Fahrenheit to Celsius. So I'm going to circle my variable of interest, that's C, highlight my other terms, 9/5 and 32, ask which one is furthest away from C. Well, that would be 32 over here. Our inverse operation will be subtract. Subtract 32 from both sides. These 32's will cancel, and we can't really simplify this left side. We just get f minus 32. This part will come down, 9 over 5 times c. So now we still need to get c by itself. We need to get rid of this 9/5. What operation is happening here? It's an implicit multiply. So how do we get rid of this? Now once again, we could divide, but that is going to give us that messy fraction over a fraction. Is there a better way we can do this? Sure, we can use the multiplicative inverse. We can multiply by the fraction flipped upside down. Multiply by 5 over 9. We're going to multiply this side by 5 over 9, but now we need to be careful because we need to multiply the whole side. So I'm going to put parentheses here to make sure we get the whole side multiplied. 5/9 times this whole thing over here. Okay, on the right, our 9's will cancel, our 5's will cancel, and we're left with just c. On the left side, we get 5 over 9 times f minus 32. And that's our answer. We've solved for c. And you can recall which properties we used to do those solving. We did the subtraction property of equality, and then we did the multiplicative inverse, as well as the multiplicative identity, right? Because these multiplied together equal 1, and then c times 1 is itself. Yeah, let's look at this one. Slope-intercept form. This should be familiar from this class. We've looked at this many times this year. This is the slope-intercept form of a line. We always have this solved for y, but now it's telling us to solve for m. There's no reason we can't do that. We can solve for any particular variable here. So I'm going to circle my variable of interest, highlight my other terms on the same side, and ask which one is furthest away from m, because that's what I want to solve for. So which one is furthest away? Looks like it's plus b. Our inverse operation will be, instead of add, we're going to subtract. Subtract b from both sides. These b's will cancel. We get y minus b, and we get mx comes down. Remember, we're still getting m by itself, so what's our last step? We have m times x. Our inverse operation will be divide by x. These x's will cancel. We get y minus b over x equals m. Notice once again, this doesn't simplify. We just get a rearranged equation with m by itself. All right, let's skip that one. We'll just do this one last problem and call it a day. This is the volume of a cone. So think about a cone. It's a circle on the bottom. We can do like a little dash here. It's a 3D object with a triangle on top. So we've got a circle. R is the radius of that circle, and H is this height right to the top of the cone. So the volume is determined by this formula, 1/3 pi r squared h. So pi is a constant, it's a number, just like any other number. It's just 3.1415, on and on and on. And we want to solve this for h. We want to solve it for the height of the cone. So this looks really complicated, but let's see if we can just take it step by step with the steps that we know. Draw our line, circle our variable, highlight our other terms. Let's get rid of these terms one at a time. So first, let's identify what operations are happening here. Well, it looks like we have multiplication, 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 and there is a square here as well. Maybe we'll have to deal with that, maybe not. Let's just deal with this 1/3 first. Okay, so we've been looking at this today. We could divide by 1/3, but maybe there's a better way. Maybe we can get rid of it by the multiplicative inverse. Multiply by 3/1. Multiply by 3/1, which really is just 3, right? 3 divided by 1 is 3. These 3's will cancel. These 1's go away. We get 3v equals pi r squared h. And we know that there's multiplication happening here as well. Okay, so let's try to get rid of the pi. We have pi times this stuff. We're still trying to get h by itself. How do we get rid of pi if we're multiplying? Well, we just divide, right? We're going to divide by pi. Divide both sides by pi. The pi's will cancel. We get 3v over pi equals r squared h. All right, our last step. We might think we need to do something with that square, but actually we're just getting h by itself. So all we need to deal with is actually this multiplication. We can just treat r squared as a number. Treat it like the number 9 or the number 13 or the number 30. R squared can just be a number. So for multiplying, our inverse operation will be dividing. Divide that side by r squared, divide that side by r squared. Okay, but now we have this mess again, right? We have a fraction over a fraction. How do we even deal with that? You might know that there's a rule that we can multiply the denominator share, but what if you don't remember that rule? What if this just looks really messy and I have a fraction over a fraction and that just doesn't compute in my head? Well, we discovered that dividing is the same thing as multiplying by the reciprocal, right? It's the same idea, right? Because we could divide by 1/3 here, or we could multiply by the reciprocal. It ended up being the same thing. So let's try that on this step. Instead of dividing again, let's try multiplying by the reciprocal. This is r squared over 1. So now I'm going to multiply by 1 over r squared. Multiply this side by 1 over r squared. These r squareds will cancel. These 1's will cancel. On the right side, I just get h. And on the left side, I actually do know how to deal with this because when you multiply fractions, you just multiply straight across. So I get 3v on top, and then I get r squared pi on the bottom. We have h by itself, so we got this all solved. H equals 3v over r squared pi. It's a little bit more complicated, but we could just go step by step using the same steps we know and solve for h. So that concludes today's objective. I can solve a literal equation for a given variable in 2 out of 2 problems.